Alan Mertens, thank you very much for doing the show.
You're welcome.
For people that probably don't know you,
there's probably millions. Yes.
probably, yeah. Of my audience, I have to just mention off the bat that Alan taught me all of my soft skills in the realm of CAD modeling. I was in high school. I was pursuing a track in mechanical engineering, and I think we had some mutual connections, and that's how you essentially volunteered to teach me CAD over the course of a couple of months, I think, once a week. So I've always been very thankful for everything you taught me, because I use it to this day, designing products, wood products, metal products. I help my dad out with construction drawings and with dimensions and plans, and so that one skill I always think of is, you teach a man to fish instead of just giving him fish, and it'll pay itself back throughout the years. So I wanted to say thanks for that.
You're welcome. And it's a really good discipline to learn, because it opens up so many things. And the software itself, if you use it, it challenges your mind. It makes you more creative. It makes you more inventive. It's a good tool for an end product, but it's also a good tool for... Sometimes it can almost be vocational. Just for the sake of creating things, you can just get into the CAD software, and it can actually be fun. For me, it's fun. Some people don't understand it. Mm-hmm. But sometimes at the weekend, if I've not got anything to do, I might just play on the CAD software just to create shapes or components or pieces, just because it's more fun than watching television sometimes.
Yeah, I agree. It gives your mind just enough tracks to expand your design and not have to remember every part of it, and lets your mind run.
Right.
And you can.
And what's even more fun recently, within the last 3 years, I've bought a pretty high-end but not mega 3D printer. Yeah. And so now, before, when you created stuff on CAD, you've got a really good 3D image of what it is you're creating, and if you've got that sort of visual perspective, you can really understand what it is. But it makes it much easier now in 3D to see what you've created, as opposed to back in the old days on the drawing board when everything was 2D. But now I can go ahead, and as soon as I make something just for the fun of it, then I can go and print it. And then several hours later or whatever, you've actually got the thing in your hand and think, oh, that's pretty cool. And there's another useless piece of something you put on your trophy shelf, you know what I mean? Yeah. But yeah, it can be fun.
Yeah, that is the beauty of modern technology, modern production. It's faster, it's cheaper, and that's been the story since the beginning of time, right?
Right.
So if you could give people a brief overview of your background and your education, we can start there, because it's...
Yeah, I can do that. That might come as a bit of a shock to most people, because it's actually a personal journey that went on, which doesn't necessarily lend itself to what people's image might be of a mechanical designer. When I left school, about the same age you were when I met you, I followed my father into British Aerospace and the Guided Weapons Division in England, and that was my basis of my engineering background. And I guess British Aerospace is something analogous to Albuquerque's Sandia National Labs. And we did what they called 6 months on and 6 months off. 6 months we went to college, and then 6 months we were at the, I guess you'd call it a factory, but it is a huge factory, like easily the same size as Sandia National Labs, with hundreds of different departments. And then the 6 months you're actually working on site, you went round and you learnt various disciplines. You learnt to work on the drawing board, you learnt to work in the fabrication shop, in the machine shop, in the tool shop. So they tried to give you a well-rounded education academically as well as, you know, practically. But, here's the but, halfway through my engineering degree, I fell in love with motor racing, and I decided, screw this, I want to become a racing driver. So I walked away and started motor racing. 3 months later, I found out that I wasn't really that good. But then it occurred to me, racing cars must come from somewhere. You know, they're not just grown on trees.
Right.
So then, after I gave up as a driver, then I became a race car designer, and this was approximately in 1976. And I enjoyed huge success as a race car designer from 76 until 2001. So that served me well, even though I didn't complete my engineering degree. And then after 2001, I retired from motor racing and went to what we used to jokingly call Civvy Street. You know, I got out of the industry and started working in mainstream engineering.
Right. Civvy Street being like the civilian world.
Well, motor racing is kind of a very closed shop. It's a large industry, but it's somewhat unique. And it obviously, all the design of the race cars culminates in motor racing with race cars run by teams, which obviously we were strongly affiliated to because they were running our product. And it's like a huge traveling circus. And, you know, we thought it was somewhat analogous to being almost like military, as a group of, I wouldn't say elite, that's a very snobbish thing to say, unique. A group of unique people, and we all thoroughly enjoyed what we did, and we all kind of set ourselves aside from general industry because I'm ashamed to say we all thought we were a bit special, you know what I mean? But of course we weren't. We were just in a unique industry. And so when I stopped in the motor racing world and I worked for companies, the first one was because I couldn't find a job, and one of the companies I worked for was actually Herrera Coaches, and I drove a bus for Martin Herrera for a year. Wow. Yeah, and then I got my first job in the commercial nuclear industry, and then that basically started off my current life as an engineer outside of the motor racing world.
So how hard is it to start racing? It sounds like you just jumped in a race car and somebody let you drive it, and that must be...
No. I wish it was that easy.
Right.
And there's thousands of would-be racing drivers that wished it was that easy. Right. Like there is in America with the Bob Bondurant School, and I think there is even a Jim Russell Racing Drivers School. Jim Russell was an ex-Formula One driver in England, and he started a series of racing drivers schools in England. And so that's how you easily get into a race car. It's not your own race car. It's not your own race team.
Yeah.
Basically, I worked like 3 jobs to try and afford to go through the Jim Russell Racing Drivers School.
Okay.
And then, you know, you go through the school, and then they've got their own domestic race car series run by the Jim Russell Racing Drivers School. And you go through that, and then once you've gone all through that, hopefully you've matured to the point, and as you've got older, made enough money that then you can finally go motor racing on your own and buy your own race car and do it. Mm-hmm. And it was that last leap that failed.
I can relate to that. So here, when I was in high school, I fell in love with a motocross bike. That was my first motorcycle. Learned how to ride a motorcycle. It was it was an 85cc 2-stroke, and it was just a handful, and it was just instantly hooked me.
Yeah.
Later in high school, I looked at street racing on a street bike.
That's scary.
You know, yes and no. The scary part is being out there with a bunch of other people. If it's just you and the bike, I've been a cautious rider, and I've never really been able to.
Yeah, but I've fallen off a bike on my own.
Oh, and I've done it too. Yeah, I mean, even when you're careful, it's like every day is different. Every corner is different.
Yeah.
But I came up against the same thing of like, there was no way that I could afford a 500 set of tires every third race.
Yeah.
So I raced, and in air quotes, I raced for about a season, and that's about as much as I could afford. And it was my dad and I would drive out on the weekends and set up a tent, and but yeah, it's here in America, you can just pay to play, and you just pay the entry fee. You go to the 1 hour mandatory safety class, and it's pretty straightforward, and they throw you in with the beginners, and they have, good rules, and but then you immediately see that if I want to continue this track,
yeah,
there's quite a bit
You've
of
got
cash.
to have big pockets.
Big pockets or a sponsor,
Yeah, I ended up in a track called Snetterton in east coast of England. Had a huge wreck and ended up over the fence into the spectator enclosure.
Mm-hmm.
And that scared me silly, to be honest. And I didn't even feel it coming. It was there on the track. Next minute, I was in the weeds, and I got the car repaired. And then driving back home from the company that repaired the car, towing it in my trailer, I got stopped for speeding. And I thought, well, the culmination of all this is just too much. I'm going to sell the damn race car and do something else.
The writing is on the wall. When,
yeah.
As you're going out the door, they kick your ass on the way out.
Yeah. Yeah. My ass was whooped. So that was it. I was done. And then And then when in '76 I joined a company called March, which was at the time the single biggest manufacturer of race cars in Europe, actually, not just England. And then the skills that I'd learned in British Aerospace came to the fore, and that to me was a dream journey thereafter, designing race cars. But like I mentioned to you earlier, originally it was all on the drawing board. And there was only 3 of us in the drawing office, which is called, in those days, it was called a drawing office. And the output of cars that March did were like 4 or 5 different categories, and would make about 140 to 160 cars a year.
Wow.
Over the winter. And we were never able to finish one design for one car. We just got the essentials down because there just wasn't enough time. And then the machinists and the fabricators used to fill in the blank gaps to finish the car.
Right.
And then we'll spend the rest of the summer catching up, reverse engineering the bits that we didn't have time to design in the first place. So it was a very busy time, but it was thoroughly enjoyable.
So that brings us to a good point. I look at, so what we do, I have a hard time categorizing what we do, because I think for the most part we're craftsmen. We build furniture. We build. We just do construction projects, small, large furniture. That's craft.
But as you demonstrated to me this morning before we started the podcast, there's a lot of engineering input into it, into your craftsmanship, because you design everything now before you actually. I wouldn't say before you actually make anything. So it's still engineering orientated. Yeah,
and that's like the mix where I think I kind of put this on a spectrum of, on the far one end is engineering, where it's very strict. The other end would just be art, you're sculpting out of clay. And I think along the middle is where you get craft, where it has some utility, but it has some free form aspects, but it has to meet rigid requirements in the physical world.
Right. Well, that's an interesting point, because the sculpting part is always something that really interested me, because it is possible to do that in CAD. If you get if you're into surface modeling, where the modeling is more organic as opposed to engineering, you can create all of those craft elements of it. but I've never been able to quite get my head around it because most of the surface modeling is not parametrically driven. It's organic, and you just have to pull shapes until you get what you want. And if you've got something which is free form but still has to have an appearance of it being an engineering product, like the specific lines of a car, for instance, you know, from an engineering point of view, you expect that to be parametrically driven, but it's not. And I have somebody, a very good friend, that does all my organic modeling for me, and he's got a flair for it. But so even though there's two ends of the spectrum, and you might think that in the middle, the craft aspect of it doesn't work, it is perfectly doable, but it's a unique head skill in itself.
I think that's well said, and that, I think for me, watching Koenigsegg go from their original hypercar into what they are doing now, where they seem to be hitting it on the engineering level, they're out of this world. On the design level, out of this world. And it's like one of those rare, just, it's alchemy almost. And to see all those elements in, you know, Koenigsegg is just an example. A lot of companies do it successfully, and I think they're just the one that sticks out in my mind, where it's so fascinating to watch.
Right. Koenigsegg is fantastic, there's no question about it. But I guess if the way I look at it is that it's not even a car to dream for, because they're so damn expensive. They're actually restricting their marketplace by the cost of their product. And I've got more admiration for people like McLaren, who still do high-tech, super sexy looking race cars that may not be in yours or mine bracket, right, cost range, but it's certainly affordable for a lot more people in the world than what a Koenigsegg might be. Oh, the Bugatti.
Right, and that's the high art world where you kind of have to maintain that image, whether it's
to justify the price.
To justify it, yeah. It's self-fulfilling prophecy, perhaps. Can you speak to motor racing as proof? I think you mentioned earlier that, you know, if you get out of a government engineering job and go to motor racing, it's almost looked as like, oh, you couldn't hack it at the high level. But motor racing, I mean, people's lives are on the line. Your job matters. You have to do it well. You can't make mistakes in the design of something, because
right. Well, I guess motor racing is a bit like Koenigsegg. We've only got a limited market, and we're in direct competition with other people that produce race cars. And not only have they got to be safe, and there's a moral obligation to make them safe because of the drivers and the pit crews that run them, but they've got to be competitive. And that's the thing that with respect, people probably don't understand the level of engineering that goes into making a race car competitive, to understand what it takes to make it competitive. Because if you don't win, you don't sell cars.
Right.
You know what I mean? Koenigsegg or McLaren can sell cars because they're sexy looking and they go fast.
Right.
They do go fast round corners, but they don't have to compete with anybody else. You know what I mean? That's the huge difference. And so there is, back in the day, it is true that race cars were simpler, but everything was simpler back in the day. You know, even where I work now, if I look historically at some of the products they produced in the past, they're way simpler than what some of the things that we're expected to do now. But that's just the advance of technology and demands on the product of what people expect of it. And so I could easily design a race car without giving it any thought at all, and it would look good and it will be functional, but it won't necessarily be competitive. Now that's the hard part, is to, when you're designing a race car, to know what you need to do to make it win, to make it competitive.
Is that the lightning in the bottle aspect, where you can get 90%, 90% of the factors to make it competitive, but is there some mysterious element that changes year to year, season to season?
I think from my perspective, and I've been lucky enough in my past to work with one of the most successful race car aerodynamicists in the world, literally in the world. And that's, to me, was the mysterious aspect of it, was the aerodynamics, which play a huge part in the competitiveness of a race car, because you can't see it. It's difficult to quantify. It's become easier these days with the rolling road wind tunnels and the load cells and the gantries that are used to measure drag and lift in pitch and heave and yaw, etc. But you can measure it, but to understand, like he does, what it is you need to produce to make it, all the machinery doesn't create the perfect aerodynamic shape. It only defines what it is you think is going to be the perfect aerodynamic shape. And I think the difference between most people and this guy, I'm totally convinced he can see air. You know, obviously not in the literal sense of the word, but he can just visualize it so strongly that he just knows that if he creates something, what effect it's going to have on the car, not just the piece itself, but also what they call the downwind effect, how the air coming off each aerodynamic device affects the rest of the car as it goes down the car until it comes out the wash in the back. Because it's not just one individual piece, it's the collective that actually makes the car fast and produce what they call the ideal lift-over drag ratio. As much lift as you can get out of it with minimal drag. So
that's an interesting point, because the variable changes at speed, and if you're racing not in a straight line, your speed's going to change every corner to corner. And it seems, so my limited experience watching motor racing and watching documentaries about all these companies, to me, it almost feels like the devices, the engineering, the componentry, it's all heading to a place where if you could perfectly adapt to every minute change on the fly, you've sort of got the shapeshifter. The ideal race car would be a shapeshifter that can, the contact patch is constant, the arrow is constant, the body adapts at any speed, at any elevation,
Yep.
And so how do you work back from that?
But the thing is, that's the whole point. The governing body of motor racing saw that coming years and decades ago.
Yeah. So that's where the
You're
rule book
not
is.
allowed to have shape-shifting race cars. The regulations say that you're not allowed to have any movable aerodynamic devices, which is difficult to enforce, because if you watch the race cars and they got an in-car camera, you can see the front wings deflecting. So it's a movable aerodynamic device which is banned. But they know that you can't make things infinitely stiff.
Right.
So they're not allowed to be movable like by computer or by driver, but with a given amount of deflection, which is governed, it can move, but that's it. And so then in motor racing, they try to make the whole car a movable aerodynamic device, not just by what you might call passive suspension, springs and dampers. They had active suspension, which basically took a lot of it away from the driver, because the pressure sensors measured, the variable aerodynamic loads through pitch and heave and roll, etc. And then it spoke to the computer, and the computer then spoke to the suspension. And so the suspension compensated for it all the time to make a stable platform to optimize the aerodynamics. But that only lasted a couple of years, and the cars became so quick that the drivers, if the system went down and the car went out of control, they couldn't catch it. So they banned that on safety grounds. So even the governing body realized that aerodynamics rule, and they're constantly trying to control that, to keep it under control, as hard as the aerodynamicists and the engineers are trying to perfect it, make it better.
That's like the other element of racing is you're competing against the other racing teams, but you're also competing against the rule book. And it's almost, you can win on the track and you can also win by exploiting the rule book, and that's just how in any sport, not just motor, but
if you read Al Unser Jr., who's a very good friend of mine who I worked with for 8 years, if you read his new book that's come out recently, he quotes in there, "It's only cheating if you get caught."
Right. And yeah, there's something to be said for it. It's there's no rule that says a dog can't play basketball, right?
And if you can train it to, fine, yeah.
Right. Do you think
I don't know how you find 6'8" tall dogs though. That could be tricky.
Well, they're too short. You can't you can't cross over a dog. Do you think there was is or was a golden era of racing where the electronics weren't so advanced, but the tires were good enough? But it seems now that tire technology is so good, computers, electronics, anything that's tied to a chip. It seems like it's changed the landscape of design, both design and racing.
Right. Well, that's a hard question, harder than you might think, because what might be considered to be the golden era of motor racing, where there was the least amount of devices to help the race car driver drive the car fast, was also the most dangerous. It was lethal. So you can't really say that was better, because they would lose a handful of drivers every year. But as the technologies have advanced, and arguably the racing has become more clinical, I still believe it's just as hard to drive a race car fast as it was back in the day, but there are more technical elements of the car which support the process of driving a race car fast, but they've become immeasurably more safe, or safer, should I say. And so, you can't say that back in the day it was the golden age because it used to kill all their drivers.
Right.
Back in the day, it might not necessarily be construed to be the golden age, but at least all the drivers, like at Silverstone, come out in one piece. You know what I mean? If they have a huge wreck, it is very, very, very safe these days.
Mm-hmm. Yeah, that is a good. It's there. The cost. There's always a cost, and it's either I think you can shift that cost around to the domain that you want it, and it sounds like we obviously prioritize the safety of people, as we should, and move it away from.
But it was also materials and technology. When I first started in motor racing, the chassis was single-skinned aluminum. Then they went to aluminum honeycomb. And then who would have thought that you could actually produce a race car out of cloth,
right?
Mold it, cook it, and it will become a supremely stiff and strong chassis. Okay. And in fact, I had that fight with the governing body of IndyCar back in the mid to late 80s, where they just refused to accept carbon honeycomb chassis because they couldn't understand the technology. Mm-hmm. And it took 2 years of experimentation and demonstration to get them to accept it, to finally give up on aluminum honeycomb chassis.
Wow.
And it was the materials and the technology, and it did cost more. It's always cost more. Nothing gets cheaper,
right?
But that's just a fact of life.
Yeah. With the pace of software technology these days, software is also cheaper and faster and better, and computers are cheaper and faster and better. How has that altered your approach, if any, to designing?
Well, a quick comment about the current situation is that you're right in every respect about the software and the hardware, but on a daily basis, it's strange now that I get frustrated if you do something and you have to wait 10 seconds for the computer to catch up with you to do a task, which back in the old days would have taken you 5 days. But you had the patience then because you were in control of your own progress. You weren't waiting on a piece of software or a machine to do it. And it just seems strange how that sense of frustration is there, and with our dependency on all this super hardware and super software. what right have we got impatient if it takes you 10 seconds longer to do something? Like I said, that back in the day, it would have taken you 5 days to do it. It's just ridiculous. It pushes us to work harder and faster. It's almost as if the machines are making demands on us. You know what I mean? It's kind of ironic.
Right.
But back in England, when I first started Galma, back in 1988, we did everything on the drawing board. You know, all the mechanical components for the race car, plus all the body work. We had a body designer there that it was still done in 2D, but we had a big wall board which was about 15 foot long down the wall, and all the body work was drawn out full size. And then all the sections throughout the bodywork were projected so they could make the patterns, and then the patterns would then be smoothed to create the 3D space. And then, like I said, all the mechanical components were done on the drawing board. But it was kind of a messy sort of process, because we had to create, it wasn't a 3D environment we created. We had to create the third dimension in 2D drawing views. But we did that by overlays. We were drawing on film, which you can actually see through, and we would lay several sheets of film over the top of each other, and then each layer would depict a different view of what you were trying to develop. And then they what we would call schemes. They weren't dimensioned. They were the size was all full scale, but the finite dimensions didn't exist as such. The basic dimensions were always in your head. And then so there was always a difficult interpretation when you interpreted that and you actually did the manufacturing drawing for each of those hundreds of components that might be on these overlaid sheets. That was when you had to decide what the actual dimension of the component was going to be, and tolerance it and dimension it to within like a few thou, plus or minus 5 thou, whatever, 3 thou. And then you had to try and retain that in your memory, such that all the associated parts that went with it all had the correct tolerances to actually mate it correctly without interference or too much slop with a partner that it was abutted to, so to speak, or screwed into, or whatever type of interface there was between the components. And then when you did that, then it had to go down to the shop floor. There wasn't any CNC machines then for machining, and the fabrication was quite rudimentary. Then the person who was making it had to interpret those drawings, and they had to have certain visual skills in their own right to be able to see that 2D drawing and then imagine in their mind what the finished product was going to be like in the third dimension when they actually made it. And so there was subsequently a lot of mistakes made, and there was also a lot of components and material wasted if it didn't work out right, and it got thrown underneath the bench, and ended up in the dumpster if it didn't quite work out right. So it was a highly inefficient and very expensive process. And then after a few years, then Autodesk came banging on our door. And I always remember their sales rep was a young girl called Katie. And she came in with her sales pitch and said, oh, no, you need to use AutoCAD to do it. And I said, why? What's AutoCAD? She said, well, it's like an electronic drawing board. You do all the things you do in a computer as opposed to on the drawing board. And I said, why? She said, it's quicker, more efficient. There'll be less mistakes. Why is there less mistakes? And I showed her how we did it. And she said, well, no, in AutoCAD, you got all those same layers like you got with the overlays of drawing on the drawing board if you want to use them. And each layer can depict a certain thing. And I said, but now we're just duplicating what we're doing, but in the computer instead. She said, but the computer has got finite geometry. it's got a finite size and geometry to it. It's not an arbitrary line you put in there. You put in a specific line at a specific place and a specific length or curvature or slope or whatever. And she said, so then, you know, it's a 2D drawing package, but then when you do go from model space to 2D space, you just transfer that information into your drawings, and then all the dimensions are there just to be populated. They've already been predetermined, and then you add the tolerances into it. So, you know, there's no guesswork as such. And I thought, oh, okay, well, that's pretty cool. So I thought, all right, we'll try it. And it was quite a leap of faith at the time because it was all quite new and it was all quite expensive. But lo and behold, a sales pitch was right. It paid for itself in the first year.
And what year was this?
This must have been about 1990, I think it was.
Okay, that's, yeah, and that's even, I didn't realize that AutoCAD had started that long ago and had a commercial product already.
Yeah.
That's pretty amazing.
Well, it was pretty amazing. What was good about it, because they saw the unique niche that they were getting into, because motor racing still is a type of environment like that. They saw it was a good advertising tool for their product. So we bought one seat and they gave us another 7, and they gave us a roll-and plotter so we could plot out all the drawings and everything. And I did a few podcasts for them and a few adverts for them, which are on television, extolling the virtues of AutoCAD.
Yeah.
And then, so the time frame it took to design a race car and the amount of scrap that went down as a consequence of it being much more accurately defined in the first place, we produced 50% less scrap, and it took us, I won't say 50% less time to design it. That's not quite true. Probably 25% less time to design it. So it was money for us across the board. It paid for itself. And then a few years later, they came along with Mechanical Desktop, which is the 3D modeling version of AutoCAD. And then, so we started to model all the race cars in 3D, and the first time we modeled them in 3D, that was the first year ever that we went from design to production with 0 mistakes, with no problems whatsoever, no scrap, nothing went wrong. And, you know, we were first able to utilize CNCs properly with the CAM software for the first time, and it was a major revelation. You know, our profit margins skyrocketed because the invent of 3D modeling then totally left the designer's third dimensional interpretation of the 2D creations he was making. He didn't have to imagine what it was. He could actually see what he was doing in 3D for the first time and put the components together in the virtual world for the first time, and that transformed into a product with no errors for the first time in the production cycle of the race car.
Wow, that's for a final product that has so many moving parts simultaneously. That's impressive. Even when I build furniture and I see the model and I double check the dimensions, you know, the odds that I can go from the model onto the CNC router and the final parts fit up, it's not 100%. It's definitely far from 100%. I still, even if I have the right dimensions.
Right, but the benefit we had that you haven't got is that there were 7 people on the design team. We're all looking over each other's shoulders, double checking each other's work.
Stages of quality control.
Stages of quality control during the design process. You know, we would have made some mistakes, but to have your peers work with you through the design process of whatever part of the project you were doing, it was easier for them to critique it because the concept was in your face straight away. It didn't take them a long time to have to absorb what you were doing it because it was right there, they could see it. And we would have made some mistakes if we didn't have that, but that's part of the teamwork. You know what I mean?
Yeah.
As I've done some work at home recently, and I don't have a team working with me, and I have made mistakes, so it's not idiot-proof like you know. I get blindsided a couple of times by things that don't work out right.
Yeah.
But back in the day, the only difference between you and me at the time is that there were a group of us working on the same product. Oh, and the other thing is, going back to the drawing board, the one thing that was supremely irritated, because this is before they invented what they call plastic lead, which doesn't smear like graphite lead does.
Oh.
And so we were creating drawings, and the drawings got all grey and mushy and everything. And if you wanted to change something, you got your eraser, and you got the erasing shield, and you have to put it on your erase a little bit out, and there'll be a brilliant white blank spot where it was. And and you know, if you're not careful, you rubbed out a lot of stuff that you didn't want to be rubbed out, and you'd have to replace it just to change the one little bit you wanted to change.
Right.
And of course, with AutoCAD on the layers, you just click on a line and it disappears. Right. It was, you know, it was so much less messy and so much quicker.
Less smeary than.
Less smeary, and there wasn't any collateral damage either.
Right. You're not. Well, the collateral damage these days is not saving in a power outage or a hard drive failure or the cloud-based, you know, sync issues where the sync gets overwritten. So there's still some smearing these days, but it's
different type of
different,
smearing.
yeah.
And with an outage, and you hadn't saved any time in the last 5 minutes, the collateral damage could be huge.
Right. It's and the other issue too is, I don't know if you ran into this, is just imperial versus metric. I don't know how prevalent that is, but software now does a good job of clearly select what you want it to be. But if you have a machine that runs on metric in the interface and you're designing an imperial, there's always going to be some, you know, it's up to the designer to remember and have the standard operating procedure is check your units, double check your units, export in the right units.
But the other thing is, export in the right units for sure. But the other thing is that if you start off in imperial and you get halfway through the design, you decide you want it to be metric, you just click a button and it all changes to metric. So just like that, you know what I mean? Even before you get to the export stage.
Right.
But going back to mechanical desktop, that was somewhat laborious, not that intuitive. But if you were proficient in AutoCAD, it wasn't too bad. But the huge leap is when they came out with Inventor, which is when you and I first met. Inventor was just mind-bogglingly way more powerful. The graphics were way more beautiful, and it was so easy to use, so much more intuitive. And that was the huge leap. And
when did finite element analysis come into the mix for these more retail products? Or for people that don't know what that is, it's essentially just analyzing stresses and in materials and designs. You can it's like the bridge calculation where you calculate, can this bridge hold, you know, X amount of semis driving over it?
I don't know.
Because when you were teaching me Inventor, it definitely had that built into it, and it was pretty amazing just to look at the.
Yeah, but then the job that I was doing when I taught you how to use Inventor, we only ever did conceptual modeling. We never did part modeling for manufacture. So there was no stress analysis. It wasn't until I continued to design race cars. Well, I said I quit from motor racing in 2001, but in 2006 and in 2012, 2006 I did a road car, and in 2006 I did another racing car on my own an inventor. And that was the first time that I used FEA. It's not as powerful as something like ANSYS or whatever, but it gives you a trend. You know, it tells you that you're headed towards a catastrophic failure, or it's going to be okay. But it's not powerful enough to give you absolute values. But then, arguably, I've never known an FAA software to give you 100% predictable absolute values on anything that you analyze with it.
Yeah, and I suppose even if it did, your metallurgy has to be also perfect. And can you source perfect titanium? Can you source perfect aluminum? Yeah, but it's expensive, and I'm not sure what the tolerance is even on that.
Right.
That brings up an interesting point that in design, and this kind of brings a human element into it. I think in images, I think in words, I can kind of do both. I can kind of picture what I want to design, and I can see it in my head. I can kind of rotate it like in my visual space.
Yeah, that's called talent. That's why you and I are good at what we do.
And so it seems like people definitely are not all granted that same level of visualization.
Right, it's what side of the brain you use, isn't it? Yeah. That's what they say. That's what the scientists say. Yeah,
right.
But I have to say my graphic abilities, if that's the right term, are stronger than my academic ones. Yeah, I'm more of a creative person than I am an analyst.
And that's interesting because you're
which is kind of good. Because, you know, as you've already observed, the software provides some of the analytical devices that you yourself might be somewhat lacking in.
Right.
So then the software manages to close the gap. It lets you be creative. It lets you be visual. And I would almost say artistic, but it almost seems wrong to confuse artistry with creativity in the design and mechanical world. But there is an element of artistry there. And then the software provides the bridge to close the gap between any deficiencies that you might have as an engineer or a designer. So, but that's good. Yeah,
I agree. That's the beautiful thing about progress and technology is it seems that year after year, it continually unlocks the ability for humans to be creative in any field.
Right. So now, of course, they've got the new module in the software now for optimization.
Oh.
So you can create a bracket and you can send it to tell the computer to optimize the design, and it will come out with what it perceives as being the ultimate design of that bracket to fulfill all its requirements in terms of its geometric shape, what it was originally intended to do, with the least amount of redundant material in it to make it as light and as stiff and as strong as it might be. And then that process is then augmented by putting it into the FEA to prove that it's optimization of your, what you might call crude component, into this beautiful looking component to verify that it actually really does what the computer's trying to tell you it's going to do. So
Right.
That's a new thing.
So there's now a circular element of the computer.
We closed the loop. Yeah.
Closing the loop on itself, and fascinating. What design projects are you working on in your own time these days? Like you said, you're still creative on the weekends, and
actually, to be honest, there's nothing at the moment other than just playing. But for the last 2 years, the CEO of McLaren Formula One team, Zach Brown, has been restoring an old Galma and a 1990 Lola that Alan Jr. won the championship in. And then Galma obviously won Indy. And he gave me the job of doing that. So I've still got people I know in the industry that are good mechanics, good people that fabricate and machining and building things. I gave them the task of the labor of restoring and rebuilding the products. But there are a lot of components on these old race cars that weren't functional anymore, and there's long since been any spares for them or any records of what those components were. So I ended up finding myself doing a lot of reverse engineering and 3D modeling the components that needed to be replaced. So then we could get them manufactured. There was one downside to this, and I say this with the greatest respect to American industry, especially locally. Nearly all of the machine and fabrication shops locally have been spoilt by Sandia National Labs, and if you go to them to make anything, it costs you a fortune. I had to get some new axles made, and the cheapest price I could get per axle locally was like $2,100 each. And I got them made in a company in Hong Kong with release spec material, 300M, fully, as you said, certified material. The splines cut, the screw threads cut, the heat treated and everything for like $630 each.
Yeah, that's a story of the last few years, maybe decade. I've seen that.
Right.
Yeah, despite how easy it is to manufacture these days and how the costs of machinery have come down so much, it's still it's still cheaper overseas. It's still oftentimes
right. But I think I don't see, because of Los Alamos and Sandia National Labs in Albuquerque, we live in an unnatural environment. Those two companies, which are government companies, seem to dictate all of our local industry. If I had a good supply chain outside of New Mexico, I could probably get better prices. But all the companies here are all spoilt because they will pay anything to get something made. You know what I mean?
It's like a monopoly problem. We've got the monopoly here is just the funded engineering. Does that make it harder for you to be creative locally, and you'd rather stick with industry contacts and you'd rather work on projects with a team? Because if it's harder to make your own, to design on your own, and is it realistic to?
Well, the projects I did on my own were the road car and then the race car. The road car we had made in Thailand. And there were 3 people here in Thailand that worked for me here and worked for the local Gallus race team that moved to Thailand to do the prototype build of the car, even though the Thailand company funded it and provided a lot of the general labor. But they were specifically 3 people that understood how to build a car from scratch and had the experience and the knowledge to do it. And then the race car, again, that was actually built in Albuquerque, and 2 of the 3 people were building that as well. So I wasn't entirely alone. I had people working with me that had the skills and the expertise to support the product. And in that same team environment, although they weren't designers, I was still able to go to them and ask them their opinions. In much the same way they could come to me and they would ask me questions, and there was a free exchange of information going backwards and forwards because we'd actually been working with each other way back in the mid-'80s, since way back in the mid-'80s. And so I didn't really find it that much of a challenge, and there was no deadlines we had to meet either.
Just so a good creative design environment.
Yeah, and it was finished when it was finished. You know what I mean?
Yeah.
So.
Well, fascinating. You've had a very interesting career. Would you call yourself a designer, engineer, or something else? What would you call yourself at the end of it all, looking back?
I'd call myself a designer, but I think over the years the roles have changed in the industry that I grew up in, motor racing. Back in the day, one person was expected to design a race car from the ground up. There were only very basic electronics in the race car to do with the engine, and all those electronics were supplied by the engine builders. But now my son works for the Alpine Formula One team. He has done for several years now. And now it's different. There's not one person is expected to design a car, obviously. Yeah. I mean, there was teams of people as I went through my career. It became more of a team process. But we all had pretty much the same engineering skills. But now, where my son Adrian works, they're very much more departmentalized. There's not jack of all trades. There's a group of specialist departments that focus on one aspect of the race car, and hopefully it all comes together in the end, so to speak.
Yeah.
So I came through an era where I'd probably be called a designer as opposed to an engineer, not to be confused with a race engineer. I don't know why it's called a race engineer, but I was also a race engineer when you actually work for a team, for a specific driver on a race-by-race basis to help him make the car go faster.
Gotcha. You're the one that dials things in and tells in specs what things need to be set at.
Yeah.
Okay.
Yeah.
Interesting.
Now I work for Sandia. I've been privileged enough to work with some people that are very, very clever, which would blow our socks off.
Yeah.
I think in the modern era, they would definitely be referred to as being engineers. And to a large extent, I provide a support role for them as a designer still. It would be fair to say that, in being humble and in all honesty.
Yeah. Excellent.
Yeah.
Thanks.
You're welcome.
To wrap up, what do you think about, we're now in the advent of the transition to electric motorsports. That's the end, right? We're going to wrap up shop, and the golden days are now, and they're coming to an end. I just saw Ducati's their new electric bike, and you can see the writing's been on the wall, but we're now finally, seems like we're getting to that point.
I'm still not convinced.
Yeah.
I know social media can often be a crock of shit, if you pardon the expression, but it's true.
Most of the time.
Yeah, but there's a lot of posts which question or argue the concept of the green car, the electric car, by virtue of the fact that all the electricity provided for the cars are still mostly come from fossil fuels. And then I saw one the other day about all the minerals that are mined to create the elements of the batteries that goes into these electric cars. And, and then you see like stupid pictures where there's an electric car, a recharging station, which is run by a generator behind it, you know what I mean, creating the electricity. It is true to say that Formula One is still at the forefront of technology when it comes to auto cars, and to a lesser but to the same extent for IndyCar racing. And I noticed that even into the 225, 226 and onwards, they're still projecting the use of hybrid cars, and they're not totally getting away from the reciprocating motor and turbochargers and intercoolers, but they're augmented by battery packs for sure. Yeah. But the electricity is generated by the engine that's in the car, You know what I mean?
Right.
It doesn't rely on an outside source.
Right.
So, and they're also trying to go towards the hydrogen-based fuels, which are cleaner. So there's hope for us yet that we won't get totally immersed in electric cars if motor racing technology refuses to go down that road. And although they've got their Formula E series, which has been quite successful, but horrible to watch, those whiny beasts.
And yeah, personally, I fell in love with a two-stroke motorcycle, and I think I'll never get that out of my soul. And just motor and the smell of oil and that's just like the romanticized picture of the motor, the internal combustion engine. Just I can't really cross over.
Yeah, I can't either, and I've still got a romanticized ideal about what my car should be. I know it could be blown off in acceleration by a Tesla, but somehow or other I still enjoy mine. I enjoy hearing the sound of the motor. I enjoy hearing the punch feeling the punch when the turbocharger kicks in. Although turbo lag is minimal these days, but you can certainly feel the sudden whoosh. You know, and it's just more. It loads the senses way much better, and it just makes the total package just more fun.
It's somehow the perfect. It syncs with the human biology somehow. The vibration, the sound, everything. And I keep reading about the internal combustion engine has so much more runway, pneumatic valves, laser ignition, electric turbochargers. I mean, there's so many. You could squeeze out so much more efficiency and still maintain the platform. And there's still innovation to be had, even though some people want to just brush it aside and say go electric and we'll figure out the energy problem later.
Well, as you know, I'm a staunch BMW fan, and if you take the so-called prestige cars of people like Porsche, Mercedes and BMW, making a token gesture towards electric cars, but I can't help feeling that they're doing it, they're being forced to do it. It's not necessarily in their genes to do it, it's not in their heart, and they're still fiercely clinging on to the thing that you and I find so exciting and will continue to do so.
I hope you're right. I do like Lamborghini's approach with the supercapacitor. Not
a flux capacitor, it's just a super one.
Just a super one, yeah. It's the modern day version of NOS. They're like, if you want something electric, here you go. Well, Alan, thank you so much for doing the podcast. Love learning about your approach to design, your history in engineering, design, racing. It's a very fascinating. I hope everybody learned something from it, and would love to talk to you again someday. And
all right, well, I'd like to thank you for indulging me. It was nice talking to you again. Long time since we last met, and I've got growing admiration for you. You're obviously a very smart guy, and I enjoyed chatting to you. Thank you.
Appreciate it. We'll do it again. Thanks.
Thank you.